Wow, another very important date for interstellar object 3I Atlas. January 22nd is coming up in less than a week, and we will have a rare geometry that gives us possibilities to maybe guys finally learn more about this thing, whatever the heck it is. So interstellar object 3I Atlas will reach an exceptionally tiny phase angle of 0.69 degrees relative to the Sun-Earth line. So picture this, guys. For 1 week in January 2026, Earth will slide into a near perfect line between the Sun and 3I Atlas. So this time it is Earth that gives us a line. 3I Atlas, an object that came from another star system, many theories what it could be. And for astronomers, we have to make clear this alignment is like basically nature briefly flopping a special X-ray mode for dust and ice. And dust and ice, that is important for what's happening with 3I Atlas. It can make the object's dust suddenly brighten in a very specific way, and that could reveal what the grains are made of and how they're built, because we know the grains are not normal. They're different because the tail and the anti-tail and the symmetric jets that we discovered are something very unusual, break physics of normal comets. So to look at that again and trying to find out what these grains are is highly important, guys. I'm excited about that. So let me explain this in normal language, because that's the entire key. I mentioned the word phase angle. So phase angle. Let's have a look at what this means and why this matters. But before that, guys, please, can you do me a favor? Click the like button of this video, click the hype button, and share it with your friends. If you can, leave me a comment, help me push this video a little bit. It helps my channel, doesn't cost you a thing. Thanks, guys. Thanks for that. Let's dive into this. The phase angle. It's a simple angle between the line from the sun to the object and the line from the sun to Earth, where we're observing 3I Atlas from, and the sun as well. So when that angle is large, we're seeing the object lit from one side. When it becomes tiny, when the angle becomes tiny, we're almost looking at the object with the sun directly behind us, like shining a flashlight from behind your head towards the dust in the air. And if you've ever done that with like fog or wildfire smoke, it reveals a stunning image. So in this case, Earth is passing almost between the sun and 3I Atlas. So that pushes the phase angle down very tiny to 0.69 degrees, which is extremely close to a perfect lineup. So 3I Atlas, it gets so close to all these perfect lineups, right? All these mysteries, all the anomalies. Guys, check my playlist. I'll put it in the end screen where I explain all these anomalies that Atlas meets. Each one of them, we've given them a probability is close to 0, but that it does all of that combined is even closer to 0 for a natural object. So we have a week-long window here, guys, and that's the whole opportunity that is so important. So I'm talking about that perfect lineup. Here's what makes it even more unusual. So it's not just a brief moment. The geometry stays very tight below 2 degrees, an angle of 2 degrees, for about a week, starting January 19th until January 26th, 2026. So we know 3I Atlas is an interstellar object, not from our solar system. What does that mean? It's not bound to the sun the way asteroids and comets usually are. So we discovered it last year, July 1st, 2025. And Atlas, by the way, because many people have asked me again, Atlas, the name comes from the asteroid terrestrial impact Last Alert System that discovered Atlas. The shortcut for that system is Atlas if you take the start letters from each word. So follow-up observations including data that were found before the official discovery of Atlas showed that it's on a hyperbolic orbit, which is the signature of something passing through from the outside of our solar system. Hyperbolic orbit. So this reported orbit has an eccentricity of roughly 6.139, way above 1, which means it's not an ellipse. It's a fly-through path. And the perihelion distance was roughly 1.35 AU. That was the closest distance to the sun. And it's also very fast. We talked about it. Its interstellar speed, when we measure it relative to the sun, it's reported at 57.7 kilometers per second. That is notably higher than any other of the famous interstellar objects. And we only had 2 others. One eye Oumuamua, 26.4 kilometers per second. Compare this to 57.7. And then Borisov, 2i Borisov, 32.3 kilometers per second. So Atlas is extremely fast in addition to all the other anomalies. So it's a genuine high-speed visitor, if we want to call it that. And it carries material from another stellar environment at best, right? Or it is even something else. And why is this alignment scientifically special? Let's talk about opposition and the opposition surge. So when the sun, the earth, and an object line up closely, we can call it near opposition because the object appears roughly opposite the sun in our sky. And if the phase angle is very small, which it is here, many dusty bodies get brighter in a way that's not just because they're closer. It's an extra boost caused by how light interacts with dust. And that boost is called opposition surge. Harvard professor Avi Loeb and his colleague Mauro Barbieri have just released a paper where they have done research on this. And basically, what is the key point from their research, it's highly interesting, is this rare alignment creates the right geometry to measure that surge for dust shed by 3i Atlas. It's potentially giving us insight into the dust's reflectivity, structure, and composition. It amazes me that we only keep hearing this from Avi Loeb and that we're not hearing this from NASA. They should be excited about this, shouldn't they? But again, if you have seen my video about the CIA releasing a letter, I showed you the letter in this video saying information about 3i Atlas is classified. Maybe you'll scratch your head a little bit. I don't want to hint at anything, but if this is just a piece of rock, why being so weird about it? Because NASA says nothing to see here, just a normal comet, nothing else, case closed. So now let's make this opposition surge simple, guys, because it sounds like a jargon, but it's actually very intuitive once you break it down. And I want to do this with you right now. So the opposition surge has 2 main causes that we have to look at. So according to Avi Loeb, 2 physical effects dominate depending on how tiny the phase angle is. We mentioned that. Number 1, shadow hiding. It's important if it's just a few degrees. So dust grains from comets, they cast tiny shadows on each other, as you can imagine. Even if they're tiny, they cast a shadow. And when you look from an angle, you see some of these shadows. They're visible. So the object looks darker. But as the sun object observer line, which is here sun object earth line, becomes more straight, those shadows tuck behind the grains from our viewpoint. That's the key message here. That's the key message. The shadows disappear and then we can see the grains Boom! I have to say it again. So fewer visible shadows means the object appears brighter, of course, right? So this effect is happening mainly with angles less than 2 degrees. We have 0.69 here. It's very tiny. It's the small angle regime. What is number 2? Coherent backscatter. It's important when the angle is extremely tiny, below 2 degrees. And it sounds complicated, guys, but I'm giving you like an easy to understand version here. Light can bounce around between dust grains along many paths. And if we have extremely small phase angles, some of those paths come in matched pairs, like a route and then the same route in reverse. And under the right conditions, those paired light waves reinforce each other when they come back towards us. That reinforcement then creates a sharp brightness spike, as you can imagine. So what they have done in their paper, they have described this as a constructive interference at very small phase angles that is tied to quantum mechanics. We don't want to go into quantum mechanics here, but I can tell you in plain words, shadow hiding means we stop seeing the dark parts made by micro shadows. And coherent backscatter, the dust briefly acts like it's aiming extra reflected light back at us through wave reinforcement. And why is finding the dust properties here, why is that the big price? Well, according to Avi Loeb and his colleague, they say that the search depends strongly on the dust's scattering albedo, written as omega 0. Okay, what does that mean? You probably might think. Scattering albedo is basically how much incoming light gets scattered back. Low omega 0 means dark material. It absorbs most light. Think like charcoal or something like that, right? Doesn't reflect back. Higher omega 0 means brighter, more reflective material. Ice fragments, for example, can do this, and comets do have them, right? So the surge amplitude depends on omega 0 and on how the dust grains are structured and packed. And now you probably might already get the point how we can learn more about 3I Atlas's dust grains here, because this is a key diagnostic in the new paper. Compact particles tend to produce a narrow surge, like half width of only a few degrees. Fluffy fractal aggregates, think like cosmic lint or something, built from many tiny pieces, they produce a broad surge, half width of tens of degrees. So if you measure not just how much it brightens, but how quickly it brightens as the angle shrinks, you can infer whether the dust is tightly packed and processed or pristine and fluffy, closer to what you'd expect from unprocessed interstellar grains, right? Tightly packed and processed would mean we have to go more towards the angle. Is this a controlled thruster or something like this? And now you might have the question, well, why couldn't we do this so well for the earlier interstellar objects that we have seen? Well, first of all, they didn't show all these anomalies. When we look at 1I Oumuamua, it didn't show that kind of gas and dust coma that you'd want for dust scattering measurements. That's one reason. 2I Borisov was only reserved at phase angles that were greater than 16 degrees, so couldn't do it. It was far from the tiny angle regime where the opposition surge is even happening, right? And it was never seen anytime, never near opposition. So the geometry and brightness on January 22nd, 2026. If we're using the object's trajectory, we see the current location here, we will have the following distances on January 22nd. Distance from the sun, 3.33 AU. Distance from Earth, 2.35 AU. Brightness, V-band magnitude, 16.7. AU means astronomical unit. 1 AU is the average Earth-Sun distance. So if it's like 3.33 AUs from the sun, it's like 3.33 times the distance that we have from Earth to Sun. If that's the distance, Earth to Sun, multiplied times 3, that's your length. That's how far it is away. V-band magnitude, we said it, a brightness of 16.7 is basically a standard measure of brightness in visible light, a specific greenish like band that astronomers are using. Bigger magnitude number is a fainter object. So we have around 16 to 7 magnitude. It's typically, it should be within reach of good ground-based telescopes, but not like with the usual casual backyard gear. So you need to have a little bit of good equipment. And interesting enough is that what they're noting about 3i Atlas, the phase angle remains smaller in later years, but of course the object gets much fainter. That would require then even bigger telescopes, right? For example, January 2027, the distance is 16 AU, and the magnitude is 24. In 2028, magnitude would be 25. So we can say this is not just like a nice to have opportunity. The 2026 window is when it's both well aligned and still bright enough to measure carefully. It's exciting, guys. And from all the other comets that we're observing, there's only one comet that has a well-measured opposition surge, and that is, in case you're interested, comet 67P Churyumov-Gerasimenko was measured by the Rosetta mission. The brightness surge is very, very small, 0.15. So the omega 0 value is very, very low. So this means very dark carbon-rich type material on this comet. And for most comets, by the way, we do not have complete surge measurements because we don't get to be able to observe them at small enough phase angles, right? So here's the elephant in the room. What could the opposition surge of 3i Atlas answer? What answer could it give us? Well, we have two major questions to be answered. Number one, the composition. Is it dark carbon dust or is it brighter icy fragments? Because we're already wondering about the jets, right? Where are they coming from? We've talked about this, the poles, and how can this be that if a natural chaotic comet that has icy fragments all over the place, it should be like chaotic and not so geometric, we have to say. So if the dust from 3i Atlas is dominated by carbonaceous material, it would have a low omega 0, roughly 0.03, or if it contains a lot of ice fragments, it would have a higher omega 0 of 0.1 to 0.3. And this is where Aviloop makes the jump towards what we've discussed earlier about this extended, extremely unusually long anti-tail that is also extremely collimated. In simple term, the anti-tail, right? Normally a comet's tail points away from the sun because sunlight and solar wind push the dust and the gas outwards. An anti-tail is an observed structure that can appear to point towards the sun due to viewing geometry, dust size distributions, and orbital plane effects. Basically, perspective and particle physics trick. But here in the case with 3i Atlas, it is not. It's real. The second question that hopefully we will get an answer is the grain structure. Is it compact and processed, or is it fluffy and pristine? If they're compact, This would imply thermal processing, like heated or altered. Hint, the aliens again. Or is it fluffy fractal aggregates, like more like pristine molecular cloud material? And that distinction matters because it's basically a clue to the life story of the dust that is coming off of 3I Atlas. So was it cooked and compacted in a disk around a star, for example, or is it more primitive, like loosely assembled and less processed? So what Eupheme and his colleagues actually recommend to everyone who's able to observe this comet, they say observe it across at least a time frame plus minus 4 days around January 22nd while the phase angle remains below 2%. Why over several days? Because comets are variable, right? Their activity can change on its own. You need multiple nights before and after the alignment so that you can separate brightness changes due to geometry, like phase angle effects, from brightness changes due to the comet's own changing activity. And they recommend using high precision relative photometry. It just means measuring the brightness very carefully. And they say you need consistency. Use the same kind of measurement setup over the time period of observation. So basically the bottom line is this unusual alignment is an extraordinary fortune, a rare geometry that may not repeat for decades because it offers a way to better characterize the dust reflectivity of 3I Atlas, the dust structure, the dust composition of 3I Atlas and interstellar material in general, right? But the data could also help in understanding the nature of the reported anti-tail jet. And that's the most crucial part because we still don't understand it. We still don't know what it is. NASA doesn't even bother listing it as an anomaly. They haven't given any explanation. They say it's a normal comet, but they can't explain all these anomalies, right? So to find out about this anti-tail jet, learn more about it, and then possibly connect it to the other anomalies, there were like 17, 18 anomalies, including the polarization properties that are referenced in this new paper. So here's what I want you to take away from all of this. Look at January 22nd. I'll keep you updated about this, right? When the geometry is almost perfectly lined up with the Sun-Earth axis. And this week is a rare natural experiment, absolutely, because at those tiny angles, the dust bodies can show this opposition surge that we now understand, this special brightening that is caused by hidden micro shadows and wave interference that boosts back scattered light. Hopefully they will measure the shape, the strength of that surge. Then we learn what the dust is like, dark carbon-rich grains or brighter ice fragments, compact processed grains or fluffy, pristine aggregates. Earlier visitors didn't give us that geometry. That's why this is, aside from all the other mysteries of 3I Atlas, a rare, do not waste it moment for the astronomy community. Hint, NASA, have a look. So guys, if you like this, thanks for liking, thanks for hyping. Click here on the end screen. I've chosen a few videos that I think might interest you. Look at these landslides. It's absolutely crazy, but always go to my start page, click on videos, click on recent, then you know what's going on in the world. Hey, stay safe, guys, and look up once in a while. You might find something interesting. Bye-bye.